Hello. Today I'm going to solve you the problem set 4 on YouTube. So let's see how this works. Okay, so there were two problems. The first problem was very simple, just one endogenous variable and different sets of instruments are used and see how they behave. So basic setup is this linear regression model and the moment function goes like this. So z is a vector, but depending on the condition in the question, the vector could be different. So in general, so this is a general form. This does not change, so I set this equation first, but this could be different. So the moment function gi takes this form, right? Nothing special, just instrument times epsilon. And q hat theta, I forgot to q hat beta takes this form with a weighting matrix W. Usually you may need to use W hat. Okay. So anyhow, under this setup, I'm going to solve all the questions under this setup. So here we are going to differentiate the moment function and plug in beta 0. And then we obtain the capital letter G, that is minus expectation instrument times xi. So again, the instrument could be different in different questions. And the dimension also, I should have, this is right. Yeah, excuse me. Yeah, this is right. And omega is the variance of the moment function at the true value of beta, which goes sigma squared and the typical ZZ prime expectation. And I used homoscedasticity here, right? And then after calculating the omega matrix, we know the optimal weight matrix is omega inverse, right? But so this is just theoretically like the weighting matrix omega, like weighting matrix W must be proportional to omega inverse. For example, like sigma squared actually does not matter. You may ignore this when you use the weight, right? Your weight does not need to be exactly omega inverse, but it is okay. It is as long as it is proportional to omega inverse, because multiplication of a positive constant does not change your minimization problem, right? So that is one possibility. And also, if the number of instruments is 1, then you don't need weight, right? There is only one. If z is a scalar, then you have only one moment condition for one parameter beta. So you don't need any weight. So these are like usually more convenient ways to implement the optimal weighting matrix. Anyhow, under the optimal weighting matrix, we know that the asymptotic variance takes this form, right? I skipped a lot of algebra. We already learned it. Sigma squared, of course, times something like this. This form will come again, so keep this in mind. Anyhow, so we derived almost everything, and we'll just plug in our instrument here, right here, 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 here. The first situation where the instrument include x itself and another instrument, and then g, the expectation big Z times X takes this form, and Z prime takes this form. So let's do the algebra. Invert the matrix to get this, right? And then multiply. So I will calculate this part first, and this part will be considered first. That is this. Okay, so the first and the 2 by 2 matrix is the inverse part, and this part is this transposed uh, instrument part, capital G. And then it equals to 1 and 0 because there is a x, right? So you are including x as an instrument for x. So only it matters, and the other instrument does not matter. So it's somehow natural. I will explain that later. And then if you multiply the last term, then you will get SXX. So expectation of x0, x squared. Therefore, the asymptotic variance, according to this formula, we just calculated this much. So plug that into here, we get this variance. That is the same variance as the OLS. Okay, so additional instrument here does not matter because x is already exogenous. Then exogenous variable, for exogenous variables, you don't need to worry about finding an instrument to make the estimator better. Here, the second example where there is only one instrument. In this case, everything is scalar, right? X times z, z squared, z times x. So we can simplify them like this. So this is what we get. So they are not matrices. And then the asymptotic variance, the second question's variance is plug that into again the previous formula, then you get this form. And in class, I explained this can be written as using the correlation coefficient rho squared. Correlation coefficient squared, right? That is the correlation coefficient between x and z. So replacing the covariance and variance of z here. Then, as you can see, because of this guy, so the other part, sigma squared divided by x, like x squared expectation, this part is just same OLS variance, but the difference is rho squared, and you know it is greater than 0 but smaller than 1. So dividing something by a number smaller than 1 will be larger. So V2 is larger than V1. In the instrumental variable regression with an endogenous regressor is less efficient than OLS exogenous regressor variable. And also another interesting thing here is they may be the same. The instrument, like endogenous variable with instrument, can do as good as the OLS when the correlation coefficient is either +1 or -1. But it is actually impossible because if the correlation is +1, that means the instrument is perfectly correlated with x. But then if x is correlated with epsilon, then automatically z would be correlated with epsilon too. So this is not possible. And the third case, now we have two instruments. So the algebra is a little bit annoying here, but we just keep doing the algebra. We have these. Then we would like to calculate this, which I skipped some lines, but just inverted, multiply this and that, like this and this twice here, pre and post, and then you will get this form. Actually, when I do it myself, I made several mistakes by myself, and also I found some mistakes in your algebra, but this is right. This is what I expected because we are going to compare, right? You first, but when you compare these two, we usually have to start from a guess. What we compare is the V2 is the asymptotic variance when you use only one instrument. V3 is when you use two instruments. So then, intuitively, V3 should be at least as good as V2, right? We are using the same instrument plus additional one, right? So we start from this. This is how I solve this problem, right? I try to show this, right? If this is not possible, something is not going well, right? I guess. Right, anyhow, so we have this inequality. Again, some algebra. Rearrange the terms and cancel out several terms, divide, factor out, and do things. Then you will get this inequality finally, right? So then you can see it's squared, and minus 2 times something. So this inequality is equivalent to this inequality. This is the left hand side is a square. So it is true. This inequality is always true, right? So we proved what we wanted. Our guess was proved. So it is correct. Now then, it is interesting. So then, like this is square, then V2 equals V3 if this was 0, right? If this was 0, then like inside the square was 0, then it will hold with equality, right? So we will discuss that later, right? Remember this. So if V2 will be strictly better than V3 if it was not equal. They were not equal. That means this is important because V2's variance is strictly greater than V3, right? So that means having another IV is better, strictly better, right? Strictly, the variance is strictly better, right? We will discuss it later after the two-stage least squares discussion. So as you see, in the end, it's pretty just a pure algebraic question, and it's simple. The algebra is not anything difficult, but if you are just careful, then you can do it. Okay, now let's do the two-stage least squares. As before, I'm going to solve out the question without, like in the general form, and then plug in the instrument at the last stage. First stage regression goes like this. So Z could be different in different situations. Gamma 0 estimated by the OLS. So OLS estimator is gamma hat, and then we know its influence function takes this form, right? So this is the influence function. And as usual, we are going to denote the fitted value this way, x0i and x hat I, depending on whether you use gamma 0 or gamma hat. So now we are going to the second stage. Second stage loss function will be written this way. So I put minus here just to make sure the first derivative does not have minus sign. So now then, the loss function is, this is the residual squared. Basically, it's residual squared. And I put negative, so it's a maximization problem now. But not a big problem. Anyhow, so I put 1 over 2 to cancel out the derivatives constant. Anyhow, if you differentiate this with respect to beta, you get this, right? Also pretty simple. Minus sign cancels out by this, and 2 cancels out 1 over 2. So this is what you get, first derivative. And what we need later for influence function is this, the derivative when beta and gamma are the true values, right? So then I will replace like gamma with gamma 0. Then this part becomes x0i, the fitted value, correct fitted value. And this is the error term, residual, using the fitted value, so which can be written in this way, right? In the class, I used UI to denote this, but I will just keep it. It's not that difficult to handle. And now differentiate the first derivative with respect to beta again, then you get this guy, right? And then we will need its expected value at the true parameter, so you get this. So this much when gamma was 0, this will become x0 squared, and then take expectation there. We get this. And then differentiate with respect to gamma transpose. By the way, like here, everything was scalar, but I used gamma transpose because in the notation in our lecture note, we used transpose, I think, right? So to maintain the same dimension, I keep the transposition here, right? As a result, we have to transpose here. This is scalar, but I have to transpose here. It is 1 by m. Like gamma is gamma transpose is 1 by m, so the left-hand side, right-hand side must be 1 by m. Scalar, 1 by m, right? And then, so this is derivative. We have two gammas, so you get two terms. But when you plug in the true values and take expectation, this part will be 0, right? The residual expectation will be 0. So this term goes away, and we only have this side. Oh, there should have been minus here. I forgot. Right? But in the end, does not matter. But anyhow, when you plug in beta 0, gamma 0, and take expectation, you get minus of this. Okay. And then we are going to use this formula. This was the influence function for the GMM. I mean, two-stage least squares, two-stage estimator, where phi is the first stage influence function, and this is the derivative of the loss function of the second stage. And then plug in all the things. I will take care of the the terms inside the parentheses, right? So the derivative takes this form, and this part g is this much. Actually, there it should be minus. I'm sorry about that. It should be minus. So this much is g, and this much is phi. And then when you combine them, you will see this part equals gamma 0. So think about this. Gamma 0 transpose z is x0i, and beta is here, psi is here, and it should have been minus. So psi part will be cancelled out. In the end, you only have x0i times epsilon. Right? Cancel. See, using this fact. And things cancel out, and we finally obtain this H inverse is here, and X epsilon here. Okay, so this is the influence function. Then from the influence function, we can tell the asymptotic variance is this, right? So this is the influence function. Its variance is the asymptotic variance of the two-stage least squares. So we get this, right? But as I said in class, x0i is just arbitrary notation. Like we are using this notation for our simplicity of the algebra. So it is not an appropriate notation in our answer, and we could like cancel out more things by replacing x0 with more underlying definition like this, right? And also gamma has its underlying definition. So try to make your answer as like based only on the foundational objects, right? Anyhow, so then you get this equal to this because x0 is gamma 0 times z, so it is squared. So I intentionally put them side by side, right? So that expectation is inside and gamma on the other side. And gamma was, again, as I said, gamma should be replaced with its underlying representation, right? This. And this is for gamma transpose. And then cancel out. So in the end, we get this. So think about this. In the end, the final asymptotic variance is sigma squared divided by this. And you remember that was what we get here. Same thing, right? That was the same variance as the GMM. So actually everything is solved. Like you don't need to do it again. Like just if you need, just plug in z to calculate them. But we already did the calculation. So algebra is the same if you need to do that. But I think there is no more algebra needed. Just plug in the correct instrument. And as I said in class, this is a very important question. And as a researcher, like when you learn the like GMM or like IV regression method, you should have had this question. What is the best IV? the more IV, the better, or when does it when does it make the estimator better? Like something like that. So, and we just answered that question in a very simple case, right? So this question was the simplest possible example to demonstrate the more IV, the better. Okay, okay. So, okay, then our answer was as long as this is not zero, then the more IVs are always helpful, right? The more IVs always better. Then how do we interpret this condition, right? Let's see. The first way to understand that is use the two-stage least square setup and think about this first stage regression, and especially like think about gamma 1 and gamma 0 for two IVs. So V is now the additional instrument, and if you calculate how we can obtain gamma 0, we get this. Think about this. This is the condition, right? So our condition says V2 is not 0, right? Hey, this is natural because when you explain the endogenous variable x, if gamma 2 was 0, that means V2 is doing nothing, right? V2 and as long as gamma 2 is not 0, V, the additional instrument V will help explain X. Okay, so that's a natural way to intuitive way to understand how the additional instrument helps explain the endogenous variable, right? Now, if you think about GMM, it is less intuitive. GMM, I will start from the influence function from the lecture note. We had this influence function, and here in particular, I'm going to look at this part. If you look at this part, G prime omega inverse, right? Then you get the same form. Actually, I was looking for this form from GMM that was here, and you get here. So this means if if the condition was satisfied, then the second moment's influence was not zero, right? So in other words, optimal weighting matrix is designed to put some weight on the second moment as long as this condition is true. Okay, so it's less intuitive. GMM is more, mechanical method, but at least like you can see how it works from the two-stage least squares uh, case. Okay, so I will do the second question in another video. Thank you for watching, and hope it helps. And if you have any questions, let me know. See you later.